This video is going to go through fluorine decoupling, how to set up the experiments, how to process the basic 1D NMR data, and how to superimpose the data to allow for the decoupling to be seen. To begin, we're going to start with the experimental setup. This will only work if the correct probe has been inserted. Contact a technician if you have any questions on how to do this, and please do not attempt to swap the probe yourself. Once we know the correct probe is in the NMR machine, we need to switch modes. For all basic NMR experiments, that walk-up mode is used. To change this, select the Options tab at the top left corner of the window and select Preferences. This should open a new window. Here, select the Tool tab at the top right corner and scroll all the way down. Here, you will be able to switch the mode by holding down with the mouse to the desired advanced mode. Finish this off by closing the window and logging in using the Data Collection button. After logging in, we can add a new sample by pressing the green plus sign in the top left corner of the screen. This is different to how samples are loaded in the walk-up mode, but it's still straightforward. Start off by writing down the name of the sample. For this experiment, the name MH957 will be used. Select the solvent that was used and the slot the sample can be found in. Finally, verify the sample by ticking the box. After the sample has been loaded, we can start running experiments. To do this, press the Create a Job for this sample button that can be found on the bottom right of the screen, followed by the Add Experiment button. This will open a new smaller window where all experiments are kept. Select the Global tab from the left-hand side of the window and scroll down to select the file of interest. For fluorine decoupling experiments, the HFX2 file contains the basic experiments that can be run, like hydrogen and carbon NMR, and the HFX2CH and HFX3CH contain advanced experiments. Click the green arrow in the top right corner to load the experiment and bring you back to the job section. Here, parameters like number of scans, relaxation time, and spinning can be changed. For the sample that is running, none of these parameters need to be changed, and therefore the Submit Job button is pressed. The experiments in the HFX2 file include a fluorine and proton decoupled carbon NMR, a fluorine NMR, a proton decoupled fluorine NMR, a standard proton NMR, and a fluorine decoupled proton NMR. I recommend also selecting a carbon NMR from the main job section, but for the purpose of this video, the experiments in the folder will be run. Don't forget to press the Submit Job button to add the jobs to the queue. Next, we can access the advanced experiments from the HFX2CH folder. A head core and HOSE will be run just as a demonstration. These experiments usually require some form of parameter changing. For the head core, the Y offset is changed to -145 ppm. This is because when opening a fluorine NMR, we can see that the chemical shift of the fluorine lies somewhere around this value. The Y sweep was also changed to 3.7 kHz per recommendation of one of the employees at JEOL. For the hosey, the Y offset was also changed to minus 145 ppm, the Y sweep to 10 ppm, and the number of points to 32. This last parameter was changed to shorten the experiment time, but if you have time on your hands, then this won't be necessary. The last thing we want to do is log out and switch back to the walk-up mode. Do this the same way we changed modes the first time round. Please remember to log back in and remove your sample using the red minus sign when your experiment has finished, as the sample slot will be locked and unavailable for use until this is done. The next thing we're going to talk about is processing 1D data. This is not supposed to be a set of detailed instructions, as there is already a video on the Canvas page that shows us how to do this. The first thing I like to do is zoom in. This is done by pressing the magnify button on the top left of the screen and selecting the area to zoom in. Next, we can set the correct reference, or change the value where the 0 value lies. Do this by zooming into the correct area and selecting the button on the top left tab. Click on the middle of the peak to set this as the reference value. Zoom out quickly by pressing the minus key. Next, correct the baseline by going into the Post-Transform tab and selecting Baseline Correct. This job will now appear in the processing list. Click on the play button to execute this job. Another thing we can fix is the phasing, that is, getting rid of these negative peaks. To do this, zoom into the area of interest and press the phasing button shown on the screen. Press down and move the mouse to the left or right to adjust the phasing. Here I'm just showing an extreme example of this. Alternatively, press the A key for this to happen automatically. Select peaks by pressing the X button on the tab, as can be seen. The program registers every peak available, and overall this looks a little messy. Clean this up by changing the baseline threshold. Press the Compute and Show Statistic button first to show the lines on the spectra, followed by the baseline button. Move the green line up to the point where above which you want peaks to be found, and press the cross button again to show the changes. Integrating is done by selecting the Integrating button on the tab. As is seen, the peaks in the 1 to 2 ppm range have all been grouped into one. Fix this by pressing the Select button and hovering over the integration box until a small pair of scissors appears. Drag this line to where you want the integration to end, and repeat this process until you're happy. Another thing we notice from the integration is the hydrogen values that the program has come up with. On this next window, the compound's NMR spectra has been loaded from ChemDraw. We can predict that the triplet present around 4 ppm belongs to the hydrogen attached to the carbon next to the oxygen. This shows up as a triplet as it's next to a methylene group, and should correspond to 2 hydrogens. To change this in our spectra, while still being in the select mode, click on the integration value, which should now appear blue, and change the value to 2 in the Normal tab in the Options list. Finally, save this newly transformed spectra by pressing File, Save As, and selecting the location and name desired. The last thing we're going to do is look at overlaying 2 spectra. This works great for emphasizing the results of fluorine decoupling. Open the files that are to be overlapped, and on the JEOL Delta tab, select the View Data Slate buttons to open up a new window. Here, select the Open Spectra button first to select the initial spectra, and the Add Spectra button to upload the second one. The Data Slate window should now contain two spectra of two different colors. Zoom into these peaks by selecting the magnifying button as before. I like to make sure the reference is correctly set before shifting one of the spectra above the other. To do this, select the Hand button from the tab and, while holding down the Alt button, click on the spectra to be moved up. The spectra can be moved as high up as desired. Here will work just fine. Zoom in to see the effect of the decoupling. As this compound is a fluorinated one, where the fluorines are attached to the benzene rings, the only change in peaks are present in the aromatic region, just as expected. Overall, fluorine decoupling are easy experiments to run, and this information can be useful when determining the structure of your compound.